This is part 1 of Chapter 6 video podcast on rangeland hydrology. So far we've looked at temperate forests and tropical forests and focusing quite a bit on the tree scale water balance, but we've also looked in the tropics, for example, at larger scales and disturbances and things. And we've also looked at the impact of human activities on forest hydrology. What I want to do now is switch gears and move to rangeland hydrology. And rangeland is just another way of saying semi-arid to arid conditions, because in lots of parts of the world, of course, most people tend to focus near rivers and coasts, but then there are people who will go and live in the vast expanses of very dry lands, particularly trying to do agriculture, bring irrigated agriculture. So 20% of people live in these dry land conditions, and cattle has been one of the main needs for getting water. In fact, when I was an undergraduate student, I spent a summer working for the Bureau of Land Management in southern Idaho, and one of the things that I helped them do, just did what I was told, but basically they would go find any wet spot where there was some vegetation or wetlands. They'd rip it out and throw in a cattle water trough or something like that. So traditionally that's been the point. Now more recently there's a lot of work in just trying to understand the dynamics between biota and water in these arid contexts, and that's really what I want to focus on in this video podcast. Ecological characteristics in the semi-arid and arid conditions. You have much more specialized conditions with the hardship of limited water, so there's fewer species that are able to live there, and there's a much more competitive, well, I shouldn't say that, but they're very conditioned to the niches that they have to deal with in those specialized dry conditions. Disturbances are infrequent, but when they come, they're usually really big and have very long and profound impacts. There's a relatively slow biological tempo, which means when a disturbance comes, it could be quite some time for the landscape to recover. And similarly with human impacts, there can be a very slow response or no response to having any kind of recovery. Okay, so the goals for this part 1 video podcast, I want to introduce you to rangeland climatic conditions and then define and illustrate key hydrological processes that exist in this setting. When we look at the Holdridge climate plant classification, we can consider that when I mean rangeland, I'm talking about precipitation of 5 to 100 centimeters of rain and temperatures greater than 0. So temperature can range quite a bit, and indeed the climate in these arid areas tends to be areas away from oceans that provide a strong buffering effect on temperature, and so you can have very large swings in temperature in deserts. So you can see here we go from dry scrub to desert scrub as we go into the drier conditions with higher potential evapotranspiration. And then you can also even have steppe or dry forest here. When we look at the water balance, we have a lot of the same terms that we always have, but just in this case, since the landscape tends to have less vegetation or fewer canopy layers, and maybe there's just scrubs or grass on the ground, then the soil is going to play a much larger role, especially with water literally evaporating out of the soil as a very large percent of the water flux. So I'm going to show you a case study using data from a 1970 study by Renard that comes from the Walnut Gulch Agricultural Research Station. So the ARS, the Agricultural Research Service, has these stations that are located all over the United States. And one of these is Walnut Gulch, which, as you can see on this map of Arizona, is in southeastern Arizona. This land cover map shows that about half of the watershed is grassland and half is brush. When you look at the monthly precipitation distribution, you can see that there are two primary periods of precipitation. One is a smaller, less important period of Pacific fronts, and the other is the primary intense precipitation that occurs with Gulf thunderstorms. If you go back and look at that climate model simulation that I showed with the tropical hydrology lecture, you can see these bands of moisture that are coming up from the south. Again, this is a United States perspective, but coming up from the south in the Gulf of Baja or potentially even from the Gulf of Mexico, and they can sweep in and provide very intense short duration thunderstorms in the dry southwestern United States. The Pacific fronts are more of what's coming straight across the Pacific that provides a lot of precipitation here in California, but in the case of southeastern Arizona, that's a relatively small component of their water balance. Virga is what we call rain that's falling out of the sky, but it actually evaporates before it can hit the ground. And this is a picture that I took. It illustrates that idea, although some of this may be hitting the ground, but just gives you a feel like these sheets of water coming down but not making it to the ground. When you look at the evaporation distribution, the x-axis here is month, y-axis is the amount of evaporation. Pan evaporation is when you take a pan, I think it's 8 feet in diameter, but I could have that wrong, could be 4 feet. You take that pan, maintain it with water, and then it can evaporate. So you're evaporating at the potential rate by having that water available. And what you can see here is there's 7 times more potential evaporation than water is actually delivered by precipitation. So even in like one of these peak precipitation months, you have 14 inches of evaporation. Well, let's see, about 25% of 14. So, a quarter of the water that would evaporate is actually precipitating. So, so what that would be, so about 3 inches of precipitation, but a potential of 14 inches of evaporation. Now this is an interesting map, so you may have to think about it for a minute, but here's a map of the watershed for Walnut Gulch, and every little circle on here is a precipitation gauge. The lines show the occurrence of equal amounts of precipitation, like this line says 0.2 inches, and then that's going all along here. So everything to the west of that is less than 0.2, but more than 0.1 inches, and then you can see that these lines get closer and closer together, and there's this real epicenter of very high precipitation that I've highlighted in red. So these lines of equal rainfall amount are called isohyettal lines. So there's a word for you for Scrabble someday. And so you can see that just this very intense storm that fell right in that one spot. So there's a very high spatial variability to precipitation in semi-arid and arid conditions. Here in California, we see that more regionally, where we can have very intense storms coming straight across from what are called atmospheric rivers, so it's a little bit different mechanism, but they can yield a lot of water in a relatively small region very quickly. I like to call these sometimes like Charlie Brown storms, because if you remember from the old cartoon Peanuts, Charlie Brown would be walking around and there'd be a cloud over his head, and that just raining on him. And so this is that same idea of a very rapidly moving storm moving across a watershed and only raining in one area. If it slows down in one spot, like you see in this map, then you can get a lot of precipitation there. If we look at the distribution of runoff, it does primarily resemble the precipitation distribution, except that most of the events from Pacific fronts and other random events just don't yield enough to overcome the soil storage capacity. And so as a result, it's only the very intense storms in July, August, and September that can produce runoff. The graph here shows the discharge through time over a period of hours, about looks like 8 hours worth of time. And so this is what we call a hydrograph. A hydrograph is a plot of discharge in a stream through time. The units here are cubic feet per second, which are commonly listed as CFS. And what you can see is there are 2 peaks here. There's a gentler peak, and then all of a sudden there's an abrupt second peak that goes a lot higher, and then it drops off. So typically what you see with a hydrograph is a more abrupt increase, which is true for both of these events, and then a more gradual decline, which you can especially see on the larger event. Now, there are some results here about trying to explain the variability in runoff throughout Walnut Gulch, for which there was no good visual representation. But what this study by Renard showed is that if you compare different areas where runoff is occurring, the vast majority of that is explained simply by the fact that you have differences in precipitation. So the areas with the highest precipitation also then have the highest runoff. But secondarily, if you have 2 areas with about the same precipitation, then the crown area of the brush, that's like the canopy for brush can cause interception storage, and so that's a secondary factor. And then whenever you're in a setting like this, it can be very difficult to measure discharge because you have to measure depths and velocities, and that's very hard to do when you have like flash flood, highly turbid water, and the channel is being reworked or eroded by those flows. One of the important processes that takes place in semi-arid and arid watersheds, and we definitely see that here in the Sierra Mountains and coastal range of California, is the idea of transmission losses. And in fact, the homework that you're going to be doing is dealing with analyzing transmission losses in the Salinas River watershed. Transmission loss is the situation when you have a hydrograph, which is shown here, at an upstream location, so flume 11, and if you take the area under this curve, if we could actually integrate that, or if you were to cut it out and weigh it on a scale, you could then calculate that you have 27.4 acre-feet of water represented by the volume of water under that curve at flume 11. As you move downstream, you would expect to have more flow because you're aggregating water from more area, but in a rangeland, that doesn't happen. Instead, you actually lose water. What we see here at flume 8 is that the peak is substantially lower and the overall volume is less than half, down to 12.85 acre-feet. By flume 6, it's been cut down to 9.28. And in fact, losses can be such a degree that at some point downstream, there may be no water at all in the river. It could be totally dry. And we've definitely seen that in many streams here in California. Well, this can be explained if we look at the groundwater condition. Normally, we have streams that are gaining. So typically, if you look at a landscape, you have high land areas that as water rains on them, some of that will go into the groundwater, and then that will infiltrate down following a pressure gradient. Or remember, we learned the word potential a few lectures ago. So the potential allows the water to flow down. But and this is hard to see because this is a two-dimensional map, but what's happening is that as the water moves down, water is being accumulated from a lot of different upland areas, and it's flowing towards the valley. And as that water bulks up from all the different locations, then the pressure under the valley is quite high. There's a lot of groundwater pressure. And as a result of that, then water tends to flow from areas of high pressure to low pressure, which means that it's going to be going up. And I really should be saying potential instead of pressure, but pressure is a component of the potential for water to flow. And so as you can see, these lines of flow direction, what we call streamlines, indicate that the water is going down in areas that are the recharge zones, and then they're coming up and the water is discharging into the stream. So this is the normal situation you see in temperate, in tropical conditions. But when you're in arid conditions, you can have either what we call losing streams or even disconnected streams. So with a losing stream, the water that's in the stream has a pressure and an elevation represented by the free surface, which is shown here. If that's higher than the water table in the groundwater zone, then the water is literally going to be flowing out of the stream into the groundwater. And you can see that with these lines that are the exact opposite from the previous slide. In a disconnected stream, the groundwater has gotten so low that the water table is now disconnected from the stream, and so water literally is percolating down through the unsaturated soil into the water table. So there could be a bulge there or not. So let's look at the overall water budget for Walnut Gulch because it's very illustrative. So you start with 12 inches of precipitation, and of that, 10 inches are stored either in the surface or infiltration that's stored in the soil. All 10 inches of that water evaporates away. So that's pretty impressive when you think about it. Like 10 out of 12 inches of precipitation are directly evaporated and transpired away. Of the 2 inches that would run off from a plot, where water is actually falling out of the sky, it's going to run off that plot. But out of that, 1 3/4 is going to go to transmission losses, with some of that going to ET and some of it going to groundwater recharge. So out of 12 inches of precipitation, only 1/4 of 1 inch is yielded as surface runoff by the time you get to the outlet. So that's just illustrates the importance of soil processes and evaporation in governing the water balance in rangelands. Now I'm going to shift gears a little bit because we have this overall course theme on disturbance, and I want to, that's so annoying, I want to illustrate the effect of channel disturbance in different climates. So if you consider a river typically has some width. Based on how much flow there is, the river will over time exist at a certain width. And so here's a river called Baseman Run, which happens to be in Maryland, and it has a width of about 15 feet. And then here's another river, that's the Patuxent River in Maryland, and it has a width of about 40 feet. Now imagine that a disturbance comes in which you have a flood. That flood is going to be shoving so much water into the channel that the channel is going to widen and expand quite a bit to accommodate that water that needs to blow through there. So you can see that the disturbance yields widening. However, once the disturbance ends, what happens is now you have dry channel areas surrounding the perennial base flow channel. And those drier areas allow vegetation to grow. As that vegetation grows, then it's going to start to accumulate sediment. As water is moving down through the system, you might have flows that are a little bit higher, and then the vegetation catches the sediment, and so over time the channel actually will narrow again and restore itself back to the long-term average. So here you can see that the time it takes, although there's no actual x-axis shown, this is indicating 10 years for Baseman Run and 15 years for the Patuxent River. Now, of course, if you have another major disturbance within that recovery time, you wouldn't have that. But as you can see, the idea here is that in a temperate climate, the recurrence interval of a disturbance is longer than the recovery time, and so there is ample opportunity to recover. So that would be the normative baseline in a temperate climate looking at channels. When you look at a semi-arid climate, we see a very different situation. So starting with a very small width, you have a large event that blows out the channel and makes a channel if it isn't there already. Like if you have maybe you have sheet wash that's taking place, and so suddenly you blow out a channel, and then before anything can happen, you have more events that cause widening, and then more events, and then maybe there's a period of recovery that takes place. And that maybe there's some attempt here to try to recover, but here we are over a 37-year period, and it hasn't gotten back to where it started. And in the case of a very arid location, what tends to happen is every time you have an event that's bigger than the last event, the channel just widens and widens and widens. So because there's like no water at all during low flows, you can't have vegetation establish and accumulate sediment and narrow the channel again. So the mechanism that's at work in a temperate river is not possible in an arid river. So this is introducing a new concept, the concept of the effect of disturbances on channels compared to some of the disturbance processes I talked about in the tropical setting. But it does illustrate the idea that this interplay between what is the interval between disturbances relative to the recovery time it takes. And when it comes to recovering the width of a channel as one indicator, in a humid or temperate condition, you can recover relatively quickly, 10, 20 years, but in semi-arid or arid, you may never recover. Okay, this is a movie that I want to show to end the first part. It was made by a colleague, Doug Duralmack from the University of Pennsylvania, and it shows essentially like a flash flood that's taking place in an arid river. You can see that in this flow, it's like a completely dry riverbed. It's not raining at all. This is the real hazard that can happen with these flash floods that take place in arid conditions. So it could be raining up in the source areas far, far away from where you are, but then that water can come down and ruin your parade if you're in the channel. I'm actually going to back up a little bit because I just want to show you, as you watch this water come down, what you can see with the flow here is that there is this snout of debris. It's a combination of sediment and a lot of sticks or woody material. That's called the snout, and then behind that is the water that's pushing that snout on. But you really get a sense of the friction as this snout is creeping along and being pushed along. Eventually the water blasts through one side preferentially, but it's really quite amazing to see these videos. And I encourage you to go onto YouTube and look for other flash flood videos in arid conditions, because the channels it's so dynamic in how it works. And you can see indeed how difficult it would be to try to measure discharge in a condition like this.